So now we have Chung-Kil Hur from Seoul National University talking about the power of imagination.
Yeah, okay, thank you. So it's time to imagine things. And so I will talk about today what's the imagination, what kind of imagination we can do in specification and verification. So what's imagination in here? So usually we have a real number, right? And then we can extend the real number to imaginary number. And we have nice property like this. We have a real number expression, but we can turn this real number into using imaginary numbers, and then we can do easy calculation in as a polynomial, and then we get back the real number result. So we can prove that cosine square plus sine square is equal to 1 using imaginary numbers easily. So let's do the same in verification and specification. So we have a real specs. We will extend real specs into imaginary specs. And then we will do similar things. And then we will extend expressibility in real spec using imaginary spec. Okay. So high-level idea is that we can start with some kind of a real spec, which can be implementation. And at the end, as a top-level spec, we want to get real spec. But in the middle, so we can have a multiple decomposition of these big proofs. Because it's a big proof and big spec, we want to decompose it horizontally and vertically. That makes each proof maybe manageable. But in the middle, we don't necessarily need to use a real spec. We can use imaginary spec, whatever it is, right? It's okay not to make sense, but anyway, mathematically, we can prove this, that's all, right? So we will introduce something in the middle. And specifically, real specs, I mean just normal behavior where you can have a non-deterministic choice. So this choose is usually called deterministic non-determinism, and then it means that you just a union of each choice. You have a behavior means a set of a sequence of I/O events or something like that. So you have for each branch you have a set of behaviors. You take a union of them. That's a usual notion of non-determinism, and that's people think it's a natural thing. That's a real spec. But then what's imaginary spec? We can take another notion of branch, which is conceptually angelic non-determinism, but we give operational meaning to it. So where you have a take, and then you have branches. Then also each branch has a set of behaviors, right? But we take intersection of them. So that's operational semantics of this take. And it sounds somehow not that natural. Why you take intersection of two behaviors? But I don't care what that means. Anyway, that's imaginary. Operational semantics, imaginary specification. And let's think about this example. So real specification, if you have choose from 1, 2, and print C, then the behavior is print 1 and print 2, print 1 or print 2, the set of behaviors. This is a set of behaviors. And then another program choosing from 2 and 3, then the resulting behavior is print 2 or print 3. Now think about this program, which now it's an imaginary choice. Take a true and false, and if it's true, I do the choose 1, 2 and print. Otherwise, choose 2 and 3, print. Then the behavior of this one, formal definition of this one is that only print 2. Because it's taking intersection. So the behavior which occurs both sides is the behavior of this program. Other behavior which occurs only one side is not the behavior of this one. Somewhat weird semantics, right? But who cares? It's imaginary. Right? So and then here, and then I will give the power of this imagination, okay? So for example, I want to prove this program refines this program. Everything is real. So orange color is real. So here, think about some module cell, which has a local storage, and there is a set and get. So set function simply take input from user, and then store it into local storage, and then get function return the stored result. Okay. And then here is some test program main, which invoke cell.set. So this function, it means that you store user input into here. And then you invoke some unknown function foo, okay? And then you get cell.get, then you get value from here, and then print x. And actually, depending on what this foo does, this may be the value set by this function or something else. Because if foo invoked cell.set inside, then what you get might not be the same as the value you set here. But I want to prove that the main function is actually just getting input and then invoking foo and then print x. So this x must be here. Then in order to prove this one, we have to know that foo.foo doesn't invoke cell.set, right? So somehow there is some assumption about foo going on. We should be able to effectively express those kind of assumptions that foo.foo doesn't invoke cell.set kind of thing. That's one thing. And also for this one, we need a separation logic. So we will do separation logic. But also we want to do modular reasoning. I want to verify this cell separately, modularly. And I want to verify main separately. And then foo, actually foo I don't want to verify. I just want to keep the same code here. And then we are going to prove the behavior refinement. The whole set of sequence of I/O events refines the whole set of the set of sequence of I/O events. So this is not partial correctness. This is full correctness. Okay. And then what can you do? First, how can I specify this one? So that's the question. So how can I specify this module, which does a set but value from user input and then get. So usually if you use the separation logic, you can say something like this. Okay, get case, you have some resource, cell X, which say that actually this module contains a value X in it, some resource predicate. And then get function, the return value should be equal to the what's specified in this resource. And then you return the same resource, so then you can access it again. But for cell, what would you say? Given cell X, because the value can be changed, right? So you cannot return cell X. But you can say, okay, there exists some R and set R, right? That's kind of a maybe natural thing, but you miss the information that actually this R is not arbitrary thing. R is a value given by the user. That information is removed, right? So I want to keep the information. And so this is a kind of natural spec, but I will use imaginary spec to retain this information. Okay, how can I do? So this is imaginary spec. So first what we do is that we operationalize every separation logic predicates using imagination. So here, you see, so this is kind of corresponding to this cell X. So we take value X, so this take is an imaginary choice. We take an intersection. And then we have some encoding of assume cell X. And this assume is a certain encoding in our system using take and choose, mixture of take and choose. We can encode it a certain way that captures separation logic idea. So we can, so this part is the precondition part. And then we can execute input function, input IO function, then you get value I. And then I guarantee cell I. So this is not the same as this one. So this part is conceptually this part is conceptually this one, but we connect that with operational semantics. So this spec exactly captures that I need this kind of resource, and then execute input, and then what I return is that is related to this input. And then get case, you just take and then cell X, and then you immediately guarantee cell X, and then return this X. So we know that the value in X in cell and the return value is the same. Okay, so we can operationalize the separation logic as a program in imaginary spec. So we can have arbitrary mixture of code and separation logic spec. Interesting thing is that this program has no argument. So it has its own standalone semantics. It has nothing to do with the other. The other program doesn't send you any information. Just some assembly function can invoke this set function. It has its own internal operational semantics. Okay, so we don't have any ghost state or whatever. Just this is all imagination. I imagine that I'm receiving certain information from the client, but client actually don't send it to you. But this is all my imagination, just something I imagine in my head. But we can operationalize that kind of imagination in code. Okay, and then what you can do is that we can prove refinement between the two using logic, separation logic kind of thing. But the result is, surprisingly, it's contextual refinement. We always get contextual refinement. It means that for any imaginary or real spec, the equal spec, if you link it together with this, then the behaviors are refined. That's our result. And then I can show you roughly how it looks. So at high level, it's just like separation logic reasoning. So when you reason about these two refinement code, you are here and you are here, for example, that case. Then you take a step, then you get the cell X in the hypothesis, in the separation logic hypothesis, and then both input, you steps same IO, And then you have to prove this one in separation logic. So it's basically looks like separation logic. So I will show you how it works. So this is the set code in the imaginary spec. You see, take Z, and then assume cell X, and then IO function, and guarantee X, and return nothing, right? And then I will prove that, so this is interaction tree code. So we allow arbitrary interaction tree. So this is refined by the implementation of Z, which looks same. But let me show you how it works. So this is the proof script. So here, so this part, sorry. This is the spec code, and this is the implementation code. Usually, implementation code will be much bigger than specification code. But in this example, this is a bit bigger. But this might be 100 lines, and you have this size, right? And then, so I take steps of L. Then I execute assume command. Okay, I executed assume command. So assume part has gone, and I have this is iris proof mode. I have this assumption cell Q1 in my iris proof mode hypothesis, so I can destruct. And also I have in the proof I need to set up the module local invariant, which looks this one. So if target contains V, then you should have auth V, which is the corresponding resource to the cell. It's a authoritative resource, and then it should be the module should contain this one, and this is a module local invariant. And then I destruct it, and then I take a step. So both sides is input, right? This is input. So you can step in parallel, and then now I do some. So now I have a auth V and cell Q1. It means that from this I know that V must be equal to Q1 somehow. Okay, so I can use the theorem, and then I have that property, and then I destruct it, and then I steps and simplify. So now my local state to change it to V return, and then I take a steps, and then or cell. So now I have to prove that. So this is guarantee part. So I have to prove that. You remember here, I have to guarantee if I execute this command, then I must prove that. So I executed that command using steps force. I think steps are force L maybe. Anyway, so I have to prove this one, right? Cell return, and then but I have a cell here, right? So I can prove this one using this resource. So that's split and eauto, and also I execute the command, right? And then I also need to prove that return value must be TT. So I can prove it. And finally, I have a return. I take step, and finally I have to reestablish the module local invariant, which is IST. And the left-hand side, the return value must be equal. That's trivial. And then I exist. The iframe, because I have auth already, and auth here. So I frame, and then eauto. So I'm done. So this proofs gives contextual refinement between the two. So our adequate theorem say that for any context, these two programs behave the same. And the meaning of this program is something imaginary. The weird the semantics taking union and intersection and so on. Okay, so we don't want to understand the exact behavior because it's just something exists. Okay. Oh, yeah. 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 Nick?
Yeah, so do the contexts include these new imaginary programs then?
Yeah, sure. Yeah.
So it's not the same contextual refinement as we would have had before.
Right. It's a stronger version. For any imaginary context, including real context, the behavior is refined. So that's all. And then now let's prove the main. Let's give an imaginary specification of main and then prove refinement. And here the imaginary spec is almost same as the original real spec, but I have this assume cell 0 because initially the client must start with the cell 0. So and then we have also for adequacy initially somehow each module should have a separating conjunction resource and they should be consistent. But anyway, this module main function requires initially cell 0, and then this is spec. But when I'm reasoning about this, I have to know about cell, right? The spec of cell. So how can we use the spec of cell and spec of get and cell? It's slightly different from separation logic because separation logic only knows about pre and post condition about set get. But now we know a bit more than pre and post condition. We also know this one. So the proof proceeds like this. We have implementation linked with the spec of the cell, and then also spec linked with spec of the cell. Okay, so this code itself is used as a spec. So we link them together. Okay, so instead, okay, so usually implementation is 100 lines. This is just 10 lines. Okay, less than 10 lines, maybe 4 lines, something like that. So the way it works is that here I inline this set code into my code. So I just execute these 4 lines. Then what I need to do is that I need to process assume and input, but this input should match with this one. So I need to process this assume here, and then assume here, and then input, and then guarantee. Then I'm coming here, and then I need to match this foo and foo. And then I also enter get, and then process assume, guarantee, and back, and then print. That's my how the reasoning goes. But interesting thing is that assume in the source side, the upper side, require you it gives I'm given this resource to me, and then guarantee in the source side means I have to prove it. But if it comes in the target side, it's dual. Assuming the target side means I have to prove it, and then guaranteeing the target side means I'm given the resource. So it's like a duality, and then it's I will quickly I won't go into detail, but it's okay. I will go. So basically same just unary separation logic is going on. From here I'm given cell, and then using this cell I can prove this cell, and then I match input, and then I'm given cell. Okay, and I'm here, and then I match foo and foo. Okay, then cell get. So I need to prove cell, but I was given this cell, so I can use that cell here. And then I'm given cell, and then come back, and I can match print, and then you can finish the proof.
Take 5 extra minutes.
Okay. 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 Yeah, good. Anyway, so that's the but I need to just a second. So I won't go into very much detail, but I can prove it. The code it looks like this. So what I said is just this one. So okay. So something like this. So that this is code. So assume guarantees are basically what I said. I can inline the spec and then do some. Okay, So this is the proof what I just said. So after this, we can have contextual refinement between the two, between this linked one and this linked one. And also, since it's contextual refinement, we have meta theory is that this library, this spec can be used by other module. So other module also do the same thing, but when I'm linking the proof together, this spec is not duplicated. They are maintained as a single module, but that's the meta theory. But the power of contextual refinement is just very big. You can compose all the proofs arbitrary ways, transitively or horizontally, vertically, all proof composes. So this contextual refinement is very powerful. And the interesting thing is that, as I said before, if foo invokes cell, then this refinement does not hold intuitively. And then if foo doesn't invoke cell, then basically what I print, in the spec, what I print is just a first input value, right? Regardless of what foo does. But here, what I print is the result of cell.get. So if foo invoked cell.set in the middle, then the value I get here and the value I get here will be different, right? Is that clear? So we have to know that foo shouldn't call it intuitively, but contextual refinement means that for any foo, this refinement holds. Okay, even if a foo invokes cell.set, this refinement holds. That's because this is imaginary spec. So let's think about, I will just tell you how it works. So if foo invokes this function, then the behavior of the program somehow matches, and then I think at this point, the behavior of this program will be empty behavior. So target will exhibit no behavior, just zero behavior, so it's trivially refined. So if foo breaks some kind of assumption I made, then somehow magically the target program becomes no B or source program becomes UB. So somehow the refinement holds. Okay, so you don't need to understand, but we proved it formally in core. So this is the fact. But in order to see how it works, even for me, it's hard. You have to think about intersection union, I'm confused. But then it works, okay? So it has very nice compositionality, okay?
Is it a good thing that it works? Is it a good thing that it works?
Why? What do you mean? Anyway, and then what we can do is that we can, since it's a compositional, fully compositional, from the previous two modular verification, if I compose them together, yes, we get this refinement result. So regardless of f, for all f, if you compose this together, you have a behavior refinement. Even if foo invokes cell.set, this refinement holds. That's just fact. Now, this semantics is something weird because some imaginary thing. So I want to now abstract into real one by eliminating this cell and then eliminating this imaginary part. So in order to prove this one, you must know that foo doesn't invoke cell. So this refinement only holds if foo doesn't invoke cell. Okay, and then also this part is in our system we can basically automate because we check every assume into guarantee, and if assume and guarantee matches, they can disappear. It's like a reaction, so it goes away. So we can eliminate all matching assume guarantee automatically, and so basically this can be automated. But anyway, so if foo doesn't invoke this one, this hold. If foo invokes this one, this refinement doesn't hold. Okay, because here, if we invoke this one, cell has assume and guarantee, but there is no matching guarantee and assume. So this assume and guarantee cannot disappear. So somehow this refinement does not hold. Okay. So finally, we can get this result using our system. Okay. And then what can I do with the imaginary spec? So I thought about more further examples, not just this simple example. I think we have many other interesting examples. So one example is logic atomicity in simple way. So usually logic atomicity is that you want to get pre and post condition in the logically atomic section. So here, this is spec of some logically atomic program. So yield is a concurrent yield point. Okay, concurrency. So this is a physically atomic section because at this point controller can go to other thread and back, and I execute this one and control go and back. So I require assume and guarantee inside of the between yield. So the position of this precondition is not the beginning of the program. If it's the beginning of program, after assumption, you have to do yield. But this one is after yield, I require assumption. So that's different. The position of this one is different. So usually, separation logic always require precondition at the beginning. That's why you need some encodings. Because the point where you provide this assumption, and then actually you use it, this mismatch. But here it matches, and then you can inline this code as if your code, then you first process this invariant of the global concurrent invariant, and then you prove this one, and then because it comes at the target, you prove this one, and you obtain this one, and then you process this invariant again. Then it's just an easy thing. So you don't need the fancy encoding of logic atomicity. And there are other things, like you can intersect of several execution models. So intersection is very interesting. Like you can intersect release acquire sequentially consistent weak memory together, and the user can choose the preferred model at allocation time dynamically. This allocation I want to use a sequentially consistent. This one I want to use a release acquire and so on. And also other things, some kind of. And we thought about this, and there are many other interesting intersection of operational semantics together with assume and guarantee. So this is all possible and gives you a nice reasoning principle. So we have some ideas, but we haven't done the work. So let's keep it secret somehow. Anyway, and also some reference implementation can be given as a specification. Reference implementation with a certain assume and guarantee can be given as a specification because sometimes you have many different software, and then you want to verify that, for example, distributed system, and each node should satisfy certain reference implementation, and then from this reference implementation, I can prove that this whole algorithm is correct. But each node does not need to reason about the algorithm itself. Just want to prove that your implementation is same as a reference implementation. Then the reference implementation can be specified. But sometimes you need some assume and guarantee. It's not completely unconditional refinement. Some assume and guarantee, conditional refinement. That's why it's called conditional contextual refinement, CCR. And okay, let's finish it. So if you go here, you have a version 1 published already CCR, but we almost finished the 3.0, which include the story what I mentioned. So the story what I mentioned is not in CCR 1.0, but 3.0, which will be soon available, we will also submit paper 2 somewhere. Okay, that's all. Thank you.
Final questions for the speaker.
Yeah. Okay.
So, I mean, several people have tried to do similar things to get this sort of vertical and horizontal compositionality.
Yeah.
And often it's sort of difficult to get, and people have to make compromises. So I know, for example, the Zhongxiao and friends, right, they have sort of limitations on objects that you can share between modules.
Yeah. Yeah.
From what I understand, you don't have that kind of limitation.
Right. We don't have such limitations because I mean we also CCR 1.0 also support only pre-post condition based reasoning without inlining. So that pre-post condition based reasoning allows a full mutual recursion. But in the inline approach, if you inline specification, then essential mutual recursion requires certain kind of induction or something. But so there's little limitation. But in practice, if you have a mutual recursion, you will use only pre and post condition, not like this inlining thing. So, and then also other limitations we don't have. We can pass pointer, so we can reason about function pointer. And here we can add weak memory. We can have a liveness, fairness, distributed network, and basically, I think we solved all the limitations of Zhongxiao's work.
I have one question, which is you have open quotes contextual close quotes refinement. And I imagine this is doing the heavy lifting, right? That there must be some actual contextual refinements that don't hold because your imaginary specifications might be sort of too expressive and might be able to observe things that actual context can't observe. Do you have an example of the sort of observation, like the imaginary observation power of these things?
No. I don't know. I'm not sure whether I understood your question properly. But okay, first, technically, this is a contextual refinement is technically correct, and then no context can observe any differences. So.
Yeah, but it's the same as my question, right? I mean, it's a stronger notion, right?
Right. It's a stronger notion, yeah.
It's incomplete, if you like. There are things that would have been contextual refinements.
No.
In the absence of
But no. The imaginary specs is the same as a real spec in terms of possible behaviors. I just took intersection. That's a set of behaviors still. It's not like adding something weird.
I think let's take this offline, but thanks again to the speaker.
Yeah.